Hello students, welcome to EPG Pathshala. I am Dr. Kajal Jindal from University of Delhi. Today we are going to discuss about the module ball milling from the paper Nanoscience and Nanotechnology. So students, let us see what we are going to learn in this module. In this module, basic principle and working of ball milling is discussed. Also, the various stages which are involved in mechanical alloying are explained in this module. Further, factors affecting the milling performance are described and the limitations are discussed in this module. Further, the advantages of ball milling technique over conventional synthesis techniques are studied in this module. Finally, the critical attributes of a grinding medium are also studied here. Ball milling is an economic and facile technique to produce nano-sized materials. It is a top-down approach of nanoparticle synthesis which includes mechanical breakdown of large substances into smaller ones. It is used in producing metallic as well as ceramic nanomaterials. In this module, the readers will learn the working principle and applications of ball mill technique in nanomaterial synthesis. The basic principle of a ball mill is very ancient. However, the machine itself could be produced only after the Industrial Revolution. Typically, ball mill is a grinder and is often employed to blend materials by grinding or crushing them for potential applications in mineral dressing processes, paints, pyrotechnics, ceramics, as well as selective laser singeing. The working of a ball mill is based on impact and attrition. The impact caused by the balls dropping from top of the shell breaks down the particle, thereby resulting in reduction in this size. Ball mill includes a hollow cylindrical shell which is rotated about its own axis. The axis of the shell is either horizontal or slightly inclined, thereby making a small angle with the horizontal. The shell is partially filled with balls. The balls form the grinding medium of the ball mill. These balls are usually made up of steel, ceramic, flint pebbles, or hard rubber. The inner wall of the shell generally contains a coating of abrasion-resistant material, for example, manganese steel or rubber. Rubber-lined or coated ball mills cause less wear to the products. The mill is nearly equal in length and diameter. In continuously operated mills, precursor material is fed from left side at an angle of 60 degree and the end product is removed from right side at 30 degrees. When the shell is rotated, the balls lift upwards on the rising side of the mill. After reaching near the top of the shell, the balls fall down, causing an impact on the particles which are trapped between these balls and the shell surface. This impact reduced the size of these particles.
Large and medium-sized mills are rotated mechanically on their axis. Small mills usually come with a cylindrical capped vessel sitting on two drive shafts which uses pulley and belt system to transfer rotary motion. Ball milling finds wide applications in pyrotechnics and for producing black powder. However, some pyrotechnic applications such as flash powder do not use ball mill due to the sensitivity to impact. Particle size can be reduced to as low as 5 nanometer in high energy mills, though they are quite expensive. Such fine particles have enormous surface area and therefore the reaction rates are greatly enhanced. Further, ball milling is widely employed in mechanical alloy manufacturing, wherein they are employed for grinding and cold welding. The rationale behind cold welding is production of alloys from powders. There exists a critical speed at which grinding occurs. This speed is described as the minimum speed which is required to rotate the balls. The working of a ball mill can be understood as follows. A powder mix is positioned in ball mill and is subjected to high energy collision by the balls. This is also shown in Figure 1. Figure 1 shows the schematics of the nanoparticle synthesis via ball milling method. The ball milling process can be summed up as: first, it consists of stainless steel chamber and several small iron, silicon carbide, hardened steel or tungsten carbide balls to rotate inside the mill. Powder of material is put in the steel chamber. The powder is reduced to nano size using ball mill. A magnet is positioned outside the chamber to apply pulling force on the material. This force raises milling energy as the milling chamber or container rotates the metallic balls. The ball and material mass ratio is generally kept at 2:1. These metallic balls impart very high energy to the powder, resulting in crushing of the powder. The ball milling process generally takes 100 to 150 hours to give uniformly crushed fine powder. It is mechanical processing technique. Consequently, the structure as well as chemical changes are caused by the mechanical energy. The size of the nanopowders produced by this technique depends on the speed of rotation of the balls, and the dimensions of 2 to 20 nanometer can be achieved. This method holds the advantage of low temperature synthesis as against the traditional methods employing high temperature synthesis for producing materials. Apart from synthesis of materials, this is a method of altering the circumstances which give rise to occurrence of chemical reactions occurring by varying the reactivity of the as-milled solids by mechanical activation, growing reaction rates, dropping reaction temperature of crushed powders, or by means of boosting chemical activities during the milling process, which is mechanochemistry. This is an approach of encouraging phase alterations in starting powders or reactants whose elements have similar chemical composition, with amorphization or polymorphic changes of compounds, disarranging of ordered alloys.
The method was devised by Benjamin in the late 1960s when he produced fine uniformly dispersed particles of various oxides such as Al2O3, Y2O3, etc. in nickel-based superalloys which could not be produced by conventional powder metallurgy. This method has revolutionized traditional synthesis techniques which mandated elevated temperature processing. In addition to synthesizing materials, this technique can modify reaction conditions. As milled solids readily undergo the chemical reactions owing to the process called mechanical activation, where the reaction rate is increased by lowering the reaction temperature of the ground powders. Additionally, chemical reactions can also occur during milling process, which is termed as mechanochemistry. High energy ball mill can also induce phase transformations in precursors such as amorphization or polymorphic transformations of compounds, disordering of ordered alloys, etc. However, all these have similar chemical composition. Alloys can be prepared by using different equipment such as attritor, planetary mill, or horizontal ball mill. The working principle for all these techniques is same. During alloy formation using ball mill, two processes simultaneously occur. One is the fracturing and the other is the cold welding of powders. Thus, it becomes imperative to create a balance between these processes for successful alloying.
In mechanical alloying, planetary ball mill is commonly employed because it involves very small quantities of precursor powders. Thus, this system is most popular for use in research laboratories. Planetary mill includes one turn disc or table around four balls. The turn disc and the ball is rotated in opposite directions to each other. The rotation of ball on its axis plus the rotation of turn disc create centrifugal forces. These centrifugal forces operate on the powder mixture and the balls, resulting in fracturing and cold welding of the powder mixture. The milling balls can attain impact energies of up to 40 times more than that caused by the gravitational acceleration in normal directions. Thus, planetary ball milling can be employed for high speed or energy milling. In high energy milling, the powder mixture is subjected to highly energetic impact. Microstructurally, mechanical alloying has four stages. First one is the initial stage. Initially, compressive forces from collisions of balls flatten the powder particles. Then, microforging causes variations in the shapes of individual particles or cluster of particles owing to repeated impact of high energy milling balls. In spite of this, such deformations of the powder cause do not effectively change the mass. Second stage is the intermediate stage. In this stage, considerable variations occur in contrast to the first stage. Powders experience considerable cold welding. The fine blending of the constituents of powder reduces the diffusion distance to few microns. The dominating processes at this stage are fracturing and cold welding. Though dissolution may occur to a certain extent, yet the alloyed powder does not have homogeneous chemical composition. The third one is the final stage. This stage exhibits marked refinement and size reduction. Microstructurally, particles appear more homogeneous at this stage. This stage marks the formation of true alloys. The final stage is the completion stage. The structure of the powder particles is tremendously deformed and is metastable. The lamellae are not resolvable via optical microscope. Alloying beyond this stage does not cause any improvement in the constituents distribution. True alloy is formed which has the same composition as the precursor.
Let us now discuss the various factors that affect the milling performance. Factors affecting the milling performance includes mill geometry, ratio of angular velocities of the planetary to the system wheel, temperature, grinding atmosphere, chemical composition of powder mixtures, chemistry of grinding tools, etc. Surface and interfacial contamination is the main problem with nanoparticles which are produced by high energy milling. This contamination may be caused by the milling tools, that is, milling balls, ambient gases, which may be traces of oxygen, nitrogen, or other rare gases which are present in the environment. Nonetheless, the milling speed and processing time can be optimized to alleviate the problem of contamination. Additionally, by coating the grinding tools with ductile materials, the chances of contamination can be reduced further. To minimize contamination from ambient gases, the powder mixture is loaded in inert glove box and then the contained powder is properly sealed by an O-ring. Aside from these concerns, other drawbacks of ball milling include long processing times, no control over particle morphology, possibilities of particle agglomeration, residual stress in the crystallized phases, etc.
Despite these limitations, high energy ball milling is extensively used due to simple design, working, and use to provide finely ground particles. Most popular application of ball milling is production of oxides of various metals for applications in sensor devices such as gas sensing. Ball mill is crucial to numerous industries as an equipment for producing extremely crushed materials. Example, cement, refractory materials, fertilizers, glass ceramic, ore dressing of ferrous as well as non-ferrous metals, etc. Ball mill can be used to grind ores and other materials which can be both wet and dry. On the basis of removal of end products, ball mill can be of two types: A. Grade type and B. Overfall type. Additionally, the grinding media can be of different types as well. The critical attributes of a grinding medium include size, density, hardness, and composition. Let us now discuss each one of these properties in details. The first one is the size. The size of the grinding media directly influences the dimensions of the produced particles. As the size of milling balls is reduced, the size of final products also decreases. However, the grinding media cannot be made infinitely small. A limitation on the size of grinding media is imposed by the size of the largest pieces of material to be crushed. Thus, the milling balls must be considerably larger than the largest particle in the powder mixture required to be ground. The second property is the density. The density of the grinding media should be more than that of the material being crushed. Third important property is the hardness. The hardness of the grinding media should be such that it is durable enough to grind the material, and it should not be very hard. Very hard media can damage the cylindrical shell at a faster pace. Another important property is the composition. Different grinding applications have different requirements. The possible presence of grinding media in the finished product is also considered, and some applications make use of this grinding media in the end product. Other applications take into consideration the reactions between the grinding media with the material being crushed. These applications include: first, if the color of produced material is important, the color as well as the material of the grinding media must be considered. Secondly, if highly pure form of product is required, then the grinding media must be selected such that it can be easily separated from the finished product. For example, steel dust, which is produced from stainless steel media, can be magnetically separated from non-ferrous products. Alternatively, the media of same material as the material being ground can be used. Next, in case of flammable products being ground, steel media can cause ignition and lead to explosion. In such cases, either wet grinding or non-sparking media, example ceramics or lead balls, can be used. Then, the certain grinding media, example iron, can react with corrosive materials. In such cases, stainless steel, ceramic, and flint grinding media are often employed. To avoid oxidation and explosion, the reactor can be filled with an inert gas, which does not react with the material being ground. Let us now study the applications of ball milling. Ball milling is extensively employed to grind materials like coal, pigments, and feldspar for poetry. Both wet and dry grinding are possible. However, wet grinding is usually done at low speeds. Ball milling increases the solid-state chemical reactivity in multiple component systems. Furthermore, it can also be used to produce amorphous materials. Coming on to the advantages of ball milling is highly advantageous over conventional synthesis techniques as it has a low installation cost. Secondly, there is low cost of grinding medium. Further, it is suitable for both batch and continuous operation. Also, ball milling is capable of both open and closed circuit grinding. Further, ball milling can be used on materials of practically any degree of hardness. So, students, let us summarize what we have learned in this module. In this module, basic principle and working of ball milling were discussed. The various stages which are involved in mechanical alloying were explained in this module. Further, the factors which affect the milling performance were described and the limitations were discussed in this module. Further, the critical attributes of a grinding medium were also studied in this module. Finally, advantages of ball milling technique over conventional synthesis techniques were studied in this module. Thank you, students, for your attention.